Hey, math people. I got a treat for you if you're taking the SAT or if you're curious and enjoy the SAT, which is a very strange and bizarre thing to be curious for. But anyway, I made an SAT math last minute cram boot camp refresher course. It is a lot of problems, a lot of review. This is designed for the few, the many that need a refresher, right? Like the reality is you're probably taking this as a junior or senior, and there's a lot of math here from freshman year, from 8th grade. A lot of math from your junior year, all across the board. It's a little over encumbering to have to memorize all these formulas day in, day out, not necessary. So the point of this video is just to refresh ourselves on all the things you've learned up to the day of the SAT. And keep in mind, it's not really all the things because every junior is at a different point in their career. Some juniors are in maybe an Algebra 2 course. Some are in as high as maybe a Calc BC course. So this is the content on the SAT. I kind of randomly specialize in SAT math videos and I know what's on it. So what I've done is I've identified, okay, well, there's actually 4 main groups of questions on the SAT. There's the Heart of Algebra group, which is mostly math that you learned in 8th grade and 9th grade, so like Algebra 1 topics, and that makes up 33% of your exam. So there's a few subtopics within that, linear equations being one of them, inequalities and systems inequality being another, what is this one? Systems of equations, and then this one right here, well, then we start the next topic. So do these 3 subtopics make up 100% of the heart of algebra? No, but it makes a pretty good percentage of it, and I'm certainly hitting all the formulas and major math ideas that you need from each of these major topics. So I have 3 subtopics for heart of algebra. So you can look this up. The SAT math has 4 major groups of questions, one being heart of algebra. The next one is problem solving and data analysis. So this one's probably the hardest to define in some ways because a lot of questions in here are less like, oh, you were taught this specific problem in the classroom, and more of, okay, here's just a scenario, here's a thing, do some number stuff with it. So this makes up 29% of the SAT. And the subtopics that I identified is subtopics that we can kind of break down a little bit more clearly, at least, are like statistics. And you can see I put that in parentheses because not everyone, actually, in fact, most students wouldn't have taken a statistics course at this point, but some ideas that are commonly found in statistics, alongside some other general problem solving and data related things like proportions, percents, and ratios. The next group of ideas come in the form of passport to advanced math. And this makes up 28% of your SAT, math SAT. And these are commonly the topics that you'll find in like a sophomore year class or a junior year class. So you got your quadratics, your polynomials, your rationals, your radicals, like actual like function stuff outside of just lines. And you know, it's kind of might be surprising to some that that's only 28% of the math SAT. So I got a few of these only because this is where a lot of the formulas and stuff come into play. So I have, looks like quadratics 1, exponentials and radical functions 2, and then 3 with polynomial and rational functions. Okay. The last major of the 4 topics is called additional topics in mathematics. It's essentially just your geometry and trigonometry. So 10%, not too crazy, right? Like you can actually kind of go without this review and you can probably figure out some triangle stuff in the heat of the moment. But it's still, I'm trying to make this all encompassing, right? Like a refresher course of this is everything that you really need to know in terms of what we taught you in the classroom kind of things. So here you'll find your triangles, your circles, your squares, some 3D shapes, and then I got another one on angles and trigonometry. Yeah, okay. So let's go through this. So it's a refresher course designed for those that, okay, it's been a minute since you last converted a parabola from vertex form to standard form, whatever the case may be. Let's get to it. Heart of algebra, our first subtopic, linear equations. So here's a little rundown. These are the simple ones. Actually, a lot, believe it or not, a third of your math SAT is primarily like 8th grade and 9th grade topics. So you'll find your simpler kind of just like solving linear equation topics here. Some necessary equations, you need to know slope, intercept, and standard form. Point slope, I don't think you need to know it, but it's nice to know. You guys can see my cursor, right? Yeah. Let's see. So visually, we can see that it takes on a line as a graph. We might see a table. And some words to look out for. Linear. The SAT will sometimes tell you, okay, hey, this is a linear function. It uses that word. If you see like per week, per minute, per year, that's usually a slope, like a constant rate of change. And those are the other two words that are necessary for that. So let's get to it. I want to do an easy, medium, and hard example of each just to, shock your system into seeing it in this setting. All these problems I wrote, they're all original problems that I wrote, but they have the same flavor that the SAT might taste like. Okay, so for an easy example, and you'll see here on the left, I might label it as a non-calculator or a multiple choice or whatever calculator for response, right? So you'll see the check mark associated with the proper one. So this is a non-calculator multiple choice. So if we have that x is equal to 3y plus 4, and we know that y is equal to 2, what is the value of 3x plus 4? Really common type of question on the SAT is maybe they make you do a thing, plug in some numbers, you get a number, but then you have to re-plug it back in to get some sort of different expression. And why do they do this? They want to see if you're reading. They want to see if you're actually paying attention. So if I know this about x. I know that x is 3y plus 4. All I need to do is just plug this 2 in for y. So I'm left with x is equal to 3, and here's my 2. Plus 4. So I'm getting an x value of 10. 3 times 2 is 6, and 6 plus 4 is 10. So what do a lot of people do here? If you're going to get this wrong, they circle C. Not 100% correct, right? What they want us to actually find is not the value of x, but the value of 3x plus 4. So if I know that, I'll use a teal color, and I'll keep this on pink. Yeah, there we go. So if I know that this value of x is 10, I can just simply plug it back into my my expression that I'm kind of actually being asked to solve for. So here it would be 3 times 10 plus 4. This comes out to 34, and you see it is choice B. SAT likes to do this thing. What is the value of? And then it's additional math at the very end. Not sure why. And you see it actually again right here. So next one, the equation of the line. So this is calculator, so we're allowed to graph this if we'd like to. In a lot of problems, just because you're able to use the calculator doesn't mean you actually should. I would say that you shouldn't touch the calculator for like a very high percentage of the calculator problems. And likewise, for a high percentage of the non-calculator problems, a calculator would be really handy. So you're going to see that pattern throughout this as well. So the equation of the line L can be written as y is equal to ax plus b. Okay, so we know that generally speaking, a line can be written in that form. You're probably more familiar with mx plus b. And this is exactly that. So we got to find the slope and we got to find the y-intercept. Now it also says what is the value of negative 4a plus 2b. How about we hunt down this a, and how about we hunt down this b, and after we get those values, plug them into this expression. So this is a free response question. Free response questions, you get like a bubble grid thing. Yeah, and usually they're situations like this, like what is the value of or something like that, right? You can't, if they're free response, you have to give a number. It's not like the next problem, which you can already see the answers for. It's an equation. Now we're going to be finding a numeric answer. Okay, so let's come up with these values. I'm going to say that the y-intercept is the easiest to find here. Looks to me like these go up by values of 1, 2, 3, 4, 5. Okay, so you can't see my cursor when I do that. So what I'm doing is I'm just counting 1, 2, 3, 4, 5. I'm just making sure it's not going up by like 2s or something like that, because that's something that can be done. I see right here is my y-intercept, and this is a y-intercept, a b value of 12. Okay, got to find my slope now. Don't want to write it that way. So I'm going to plug that in for that coefficient in a second. So slope to me is, we can find it going from maybe like the y-intercept to the x-intercept if you like, and do this like massive triangle. It's down 12, right 16. And that's nothing crazy. Rise over run, negative 12 over 16 is negative 3 over 4. You could also, if you didn't like that, you can go, you can kind of pick some other points on the inside. So I'm trying to find what the next point would be. Oh, okay, here it is. It took me a minute to find that. You could also alternatively think of it as like maybe the smaller triangle. This is down 1, 2, 3, right 1, 2, 3, 4. So you'll see negative 3 over 4, same thing. You just don't have to reduce it. So that's what my slope is here, negative 3 over 4. I have what my a value is, negative 3 over 4, and I have what my b value is, positive 12. We just have to plug these into this expression. So plugging this in for a, plugging this in for b, and we'll hunt down this expression. So negative 4 times negative 3 over 4. And then plus 2 times 12. So I do get a calculator. If you wanted to use a this would be like the one moment where using a calculator would technically be fine, but I don't know. I would say try to avoid it, because sometimes the clicking and clacking can take more time than just doing it mentally. But who knows? You do you. I see these 4's cancel. I see these negatives cancel. So I'm left with 3 plus 24, getting a final answer here of 27. Okay, so the next one, the harder example, looks like we do have access to a calculator if we choose to use it, and then multiple choice. So there's a lot of wordy problems on the SAT, a ton of them. So you have to know how to read. Reading is an important skill. But what I recommend is to really cut the clutter, like mentally, and not get over encumbered by just the amount of blah. Because in a lot of cases, they throw you into some scenario and you're like, quick, you're an architect. You're trying to figure out, it's 1986 and you're trying to figure out the weight of a dinosaur bone, and you have this other dinosaur bone as reference, and you know that the weight, and you're like, whoa, whoa, whoa. And I'm just a junior taking the SAT, and this is just number 17 on the 4th portion of the math SAT. And then you solve that problem, and then you go on to the next problem. It's like, okay, but what's the equation of this line? So you're like, but wasn't I just an architect in the 80s or something? So try not to get too whiplashed around with problems like this. I see some words. What I actually do when I see scenarios like this is I actually do just look at the answers really briefly. And I just think to myself, okay, well, clearly here I'm going to be writing some sort of mx plus b linear function. That's what I'm gathering by just looking off the answers. So I'm going to be thrown into this ridiculous scenario. Mathman held on to some rare items in a video game he plays so that he can sell them 6 months later when the demand is high. Okay, so he's trying to make some money off of a game. The provided table shows that each item's value on release and 6 months later. Okay, so that's kind of just describing what the table is. The relationship between an item's value 6 months later, S, okay, so that's, I guess, this column, that's the output, sure, is in dollars, and the item's value on release, R, okay, that's your input, in dollars, can be represented by a linear function. It's so wordy. Get used to this. Try to extract what it's really looking for. What is it really looking for? You didn't need to read any of this. This situation is ridiculous. Look at the names of these items. What is a wee-woo laser? Doesn't matter. And you're going to see a ton of these, both on the SAT and on this with me. So what is it really asking you to do? Simply come up with an equation that represents this scenario. Work off the answers. I noticed that in this, do I have a highlighter tool? I don't have a highlighter tool? Markup? No, I do have a highlighter tool. Okay, so I noticed that the answers here all have a different slope. Sometimes you'll see maybe 2 have the same slope and another 2 have the same slope. and like maybe the difference is in like their b-value or something like that. It depends on how the problem is written. So you don't have to solve, since we have the answers at our disposal, you don't have to solve every last aspect of a problem. Here, if we simply find the slope, that is all we need. We don't have to set up some fancy equation with all this blah going on. I can simply find the slope. This is just a table, and so long as I identify what the slope is, that's enough. I don't care about whatever that y-intercept may be. So I'm going to do that right now. Let's find the slope. I'm going to just kind of pick, and it looks like I do have access to a calculator. I see this value right here with a 0.5. As a result, I'm not even going to look at this ordered pair because I don't want to deal with decimals. I want to find the slope using the galactic shooter and the wee woo laser. So I know that slope. Oh, and that's another formula. I'll make sure to add that. So the other formula you should know is, see, there's just a lot of stuff, right? I mean, this is supposed to represent like kind of the foundation of all your maths you learned in the course of your essentially like middle school up to high school up to your junior year. So you should know slope formula. But I guess that was kind of implied with the words here. So the slope formula for this, we can use change in y over change in x. So I'm going to just write difference in y over difference in x. And I'm going to use these as my y values and these as my x values. So I will use I'll do this. I'll say that my x sub 1 comma y sub 1 is going to be the galactic shooter. It'll be 86 comma 119. And then my x sub 2 comma y sub 2, this will be my wee woo laser. This will be 190 comma 275. So I'm literally just plugging this into my formula, and if I get a slope of 1.15, then D is the answer. But let's see what it actually is. So y sub 2 is 275. My y sub 1 is 119. And I guess we can use a calculator for this, which is nice. My x sub 2 is 190, and my x sub 1 is 86. So just using slope formula. Yeah, I'm gonna use a calculator for this one. So 275. You guys can't see what I'm typing, but I'm just doing the math for this. Minus 119. So this is coming out to 156 up top. And then down below 190 minus 86. That's 104. So I can just continue to use my calculator to figure out what this fraction is. 156 over 104. This comes out to 1.5. Do I have a slope here of 1.5? I sure do. It's in choice A, and I'm done. I don't care about what that y-intercept is. I can utilize the answers to my advantage. I see they all have different slopes. By process of elimination, all the other choices are wrong. Done. All right, next one, inequalities. So these are still linear in a lot of cases, not all. And you still need to know the slope-intercept and standard form. Understand what these symbols mean. So greater than or equal to has the line underneath it. Greater than does not. Less than or equal to has the line underneath it. Less than does not. So if you don't have that line underneath, that means you do not include that moment where they're the same on both ends. If it does have a line underneath, you do. And I don't really see it too often graphically, but this is what a system of linear inequalities might look like. We see the dashed line here. This is for when you have a less than or greater than, and then the solid line is when you have the or equal to. And then, like in language, oh, I meant to highlight, but that's not what I want. In language, know how to, okay, if I see no more than 10, no more than 10 would mean x is less than or equal to 10, right? You can be 10, 10's okay, but you can't be any more than it. Whereas like less than 10, I wouldn't include that 10 as well, right? 10 is not less than 10, but 10 is no more than 10. So knowing how to like convert language into mathematical notation through inequalities. So these are just some examples of what you may see. All right, first easy example, no calculator multiple choice. Which of the following inequalities is equivalent to this expression? Okay, what's really tempting to do here is to immediately start solving for y. Don't do that. I'm going to look at my answer choices here, and it looks like only 2 of them are solved out for y, and the other 2 are some kind of standard form-esque setup. So what's the deal with that? We should perform some algebra to try to create one of these scenarios. Yes, we might have to solve for y. But I don't see us ever solving for x here. I also see that there is already two, and I'm using my mouse right now. There's two here that are in this like standard form setup. How about on my way to solving it for y, I kind of just try to run into a standard form setup that could be one of these two. Because if it isn't one of them, then sure, I have to solve for y, and then choices B or C might be my answer. But I notice here that I have a 1 leading coefficient here. If I try to divide everything by 12, 16 over 12. So let's just attempt to do that. I'm going to do this in pink. This is going to be the wrong solution, and I'm going to erase it thereafter. If I divide all these by 12, not going to work out for me because I'm going to get x minus, I don't know what that is, 4 over 3? Yeah, 4 over 3y, and that's going to be over, or less than or equal to 16. I can divide both sides by 4, so it'd be 8 over 3. Yeah, that's not that. So I'm going to just cross that one off. I guess I'll keep my work here just to eliminate that. But I do see in D, 12 divided by 4 is 3. 12 divided by 4 is 3. 16 divided by 4 is 4. So that might actually be it. So I'm going to rewrite the expression here. 12x minus, and I'll put a sad face here. Like, oh no, I tried this approach, didn't work. Right? I'm trying to go through this as authentically as possible, even though I wrote this. So 12x minus 16y is less than or equal to 32. I notice the coefficient goes from a 12 to a 3. How do I do that? I divide by 4. So I'm going to divide everything by 4. Divide by 4, divide by 4, divide by 4. And maybe I might get lucky, and then that's the answer. And this was really secretly just a one-step problem. 12 over 4 is 3. 16 over 4 is 4. And 32 over 4 is 8. We have ourselves a winner. Smiley face for that one. So what if that didn't work? I would say, oh shoot. And I would just continue to solve. I would probably move over that 3x and divide by -4 and try to get it in mx plus b form. But I didn't have to do that, so lucky me. We're moving on. All right, next one. This is a fun, I do like this one. In this equation below, x is a positive number and y is a negative number. Which of the following must be true? Okay, so it's tempting to do one of two things, depending on how your mind works. It's tempting to try to create some sort of like generalized expression and prove it in kind of crazy way. It's tempting if you're a math-minded person to do that. In a situation like this, though, for majority of us that are just kind of like trying to take an SAT and just get it over with, just plug in numbers and see if it works or not. So if x is some positive number, okay, maybe x is 3. And y is some negative number. All right, maybe y is -2. Which of the following must be true? Let's just plug these numbers in and see what happens. So I would get z here is equal to, it'll be 3 over, so it's going to be -2. I want to use pink for that. And then it looks like it'll be a -3 because there was already a minus here in front of this x. So in this particular case, when x is 3 and y is -2, I end up getting, what is that, 3 over negative, so it's going to be a negative number, -3 over 5. Okay, so in this particular case, -3 over 5, I see a negative number. I could run through a few examples of this, or I can just kind of think, well, my top is always going to be a positive number because x is positive. My bottom is always going to be a negative number as well because y is negative and we're subtracting off a positive number, which is making it further negative. So no matter what I plug in, I'm always going to shoot out a negative number. So since I'm getting a negative number here and I'm always going to be getting a negative number, let's think about the answers now. So in this particular problem, I didn't really look at the answers too much at the start, but you could have kind of just quickly glanced at them. Some relationship with 1, maybe. We have a 0 in there. So which of these is true? Do we always get z as 0? No, so I'm going to cross that one out. Do we always get z as 1? Clearly here, no. We are going to cross it out. So ultimately, we're always going to be getting a negative number. So the, I guess, most strict inequality that would work best here would be like z is less than 0. But of these two, And it looks like they're not going in for any sort of me strictness here. Like, okay, always negative, so z would always be less than 0. But which of these, it must be true. So if you're always less than 0, then you're certainly always less than 1. So this would be my answer choice here, D. I would also cross out C as well. Reason being, we're not greater than 1 here. So even with just this singular example we've done, that was enough for us to eliminate 3 of 4 of the options, leaving us to have an answer for stat D. Okay, next one, a little bit of reading. It's what it is. Pet store employee. And okay, well, stepping it back. Maybe should have practiced this in the last one out loud. But like I said, it's especially when there's a lot of writing. This last one didn't have a lot of writing. Especially when there's a lot of writing, always look at the answers just so you have an idea of what the end game is, right? Because as I can just tell, we're being thrown into some ridiculous scenario where we're a pet store employee trying to meet our supervisor's conditions. What's going on? This is just a random question on the SAT. Whiplash City. But if I'm looking at the answers here, it looks like I just have to create some sort of system, and the inequalities just change every time. So I don't have to think about the algebraic setup at all. I simply have to come up with the difference in the inequalities. Okay, so I'm kind of grounded for what my expectation is as an SAT student, which is the reality of the case. So a pet store employee is trying to meet the criteria for her supervisor that her supervisor created for her. The store must contain at least 40 cats and dogs. So if we think about what at least is, that means that 40 is okay, but we want to be above it. So we want to be greater than or equal to 40. I can already eliminate some of these options here. So I see, maybe I'll do this. So in pink, this is this kind of condition right here. And I'm not even going to really necessarily pay too much attention to the expression on the left for now. I just know that I need to be greater than or equal to 40 some way, somehow. So here we see that this passes this condition, and this one fails. And likewise, this one also fails, but this one passes. So I'm already between A and D. And I haven't even finished reading half the problem. Okay, but they cost money to maintain. Each dog costs $3 a day, and each cat costs $2 for like food-related stuff, presumably. The store can only afford to spend, okay, so we have to think about this one, can only afford to spend $200 a day. What would that imply? If you can only afford to spend, like, at most, there it is, that's the word, $200 a day, that means that you don't want to exceed that amount. So if we look through these, we'll see of the two, well, actually, in this case, they're both less than 200. So kind of like an oh shoot kind of thing. Like that didn't really actually help me in that sense. So which system best represents this? Okay, I was kind of hoping that sometimes that will happen. Sometimes that will happen where the inequalities tell 100% of the story. In this case, it didn't. So we do still have to decide between the two. It looks to me like the expressions flip-flop. So we do need to know a little bit about the expressions here. C plus D, so that would be cats and dogs, need to be greater than or equal to 40. Where here we're saying cats and dogs together need to be less than 200. 2 is less than 200, yet that doesn't meet the criteria of in pink. You'll notice that the expressions are flip-flopped. The money equation is this, or inequality is this 2C plus 3D. And that's where the 200 should be associated with. So you'll note here they accidentally flip-flopped our numbers for D. So you did have to know a little bit about the expression of the matter. Sometimes with these setups, 100% of the work is on the inequality. Here, maybe 60% of the work was on the inequality. In D, they flip-flopped the numbers that were supposed to be associated with the two. The 200 should have been associated with the $2 for each cat and $3 for every dog. So in which case, A is our choice for that reason. So inequalities here, not too crazy, still a part of that heart of algebra kind of idea. Okay, so next one being systems of equations. Another heart of algebra. Still need to know an equation of a line, still need to know standard form, and know that a solution to a system is where they intersect. And you might see some language like, okay, the system of equations above has solution x comma y. So this language is pretty common on the SAT, just to prompt you like, hey, by the way, you're about to do a systems problem. All right, so next one up, easy example, calculator for response. calculator could be a bait. So I see here the solution x comma y to the system is the solution to the system of equations. What is the value of 2x? Okay, so what I could do is I can find the point of intersection, and I would get an x value and then plug it back in for x in the expression 2x, so double it, and that would be my answer. Okay, and if you want to do it the extra super slow way, you'd use a calculator, so you'd have your TI-83, and you would plot these, and I just kind of want to show it for the sake of showing it. And you would plot your y is equal to 2, and you would plot your, well, actually, you would have to even solve for y on the second equation. So I'm intentionally showing it the slow way because I think we can learn off this. So I'd have to do, okay, so I'll do kind of slow way. Slow way. I have this 2x plus 4y is equal to 20. Okay, subtract the 2x from both sides. You get 4y is equal to negative 2x plus 20, and divide everything by 4. So you get y is equal to negative 1/2 x plus 5. And then you can graph that on your TI. Y is equal to negative 1/2 x plus 5. Okay, and then I can come up with my solution here, which, by the way, it's a lot more painful on a TI-84. You have to do like second intersect, find the first equation, enter, second equation, enter, enter again. It'll find your ordered pair. It could be an approximation. I mean, this technology is ancient. I wonder if this video will still be around when like Texas Instrument 84 calculators aren't used anymore, and we use like a program like Desmos. That'd be crazy if this video will still be relevant by then. So we end up getting a solution of 6 comma 2, and our x value is 6, so 2 times 6 is 12. This is the slow way, which is fine. But we can try to be clever. In a lot of situations that are calculator-based, the calculator is a bit of a trap. It helps you more than it hurts you if you're leaning too heavily on it, because the reality of the fact is a lot of our kids do that in the classroom. So they're kind of capitalizing and taking advantage of that, which sounds kind of evil. How would I do this in a more efficient way? I notice that 2x is right here. I notice that a 2x is literally right there. So the faster way, and maybe I'll just do color coding for this, faster way is to take this 2, plug it on in, and solve for the 2x. So I'm going to get 2x plus, okay, so it'll be 4 times 2. Sure, that's an 8. That's going to be equal to 20. Move that 8 over, so I get 2x is equal to, well, it'd be 8. So 20 minus 8 is 12. And I don't even have to solve for x here, because I'm being asked for the expression 2x in the first place. So there's a 12, that is your answer. And notice how much faster that was. SAT is loaded with quicker ways of solving problems like this, because reality of the fact is they know some people are going to spend 80 seconds on this problem. Some people are going to spend 20 seconds on this problem. Where's that other 60 seconds going to go? It's going to go into a longer, wordier problem. So the faster student on this problem is going to have more time on a wordier problem, where the slower student may have to guess on that one. So it ends up hurting them later on the test. This test is always created with all these things in mind. Always. They're cleverly written. So I do respect the writers in that sense, but it does feel kind of evil from the student end of things. I get that. Okay, so the answer there was just 12. Okay, keeping this train moving. So for the solution xy to the system of equations. Yeah, that's going to happen. Didn't proofread this. What is the value of x plus y when x is greater than 0? Looks like I cannot use a calculator, because to me I see a parabola and I see a line. So it would look something like you got a parabola and we'd have like a line going through it. I know that it's going to look something like that. Okay, but we want to figure out when, so it's going to cross through twice, when specifically our solution has an x value greater than 0. So it looks to me like we're going to have some negative x solution that I'll do in maybe teal here, and then we'll have some maybe positive x solution, which I'll do in pink. I don't need to actually know what that looks like graphically, but I just want to provide some sort of background intuition behind it. I'm going to get two answers is what I'm trying to say. Okay, so I got to solve this algebraically. I know that y is equal to x squared, so why don't I just sub this on in? Maybe I'll just do this on red because I already borrowed those colors. So I want to take this x squared and I want to plug it into this y. The negative 5x stays, the 2 stays. I'm going to be writing an x squared now in place of the y. And this is equal to 3. I see a quadratic. Uh-oh. So this was kind of secretly a quadratic problem at the same time. I'm going to write this in ax squared plus bx plus c form, because this is going to allow me to see maybe I have to use a quadratic formula. Maybe I can factor it. Who knows? I'm going to move the 3 to the left. So it's going to be 2x squared minus 5y minus 3. And that's equal to 0. So can I solve this by factoring? There are so many different ways of factoring this that it's insane. Depending on who you were taught by, what method you were taught, there's a lot of different ways. I'm going to do the most common approach right now. I think some teachers back in the day used to call it like AC rainbow method, because you kind of take the product of A and C, and then we could do like a box method approach. Guys, there are so many different ways to factor. It's actually insane. But I'm going to just kind of do it my like grouping way using AC method. So I'm going to take 2 times negative 3. So you factor this however you like is what I'm trying to say. And that's negative 6. What 2 numbers multiply in the negative 6 and add into negative 5x? So 3 and 2 are tempting, but I need to add into a negative 5, so they both have to be negative, and that's not good for negative 6. What about 3 and, or what about 6 and 1? So I'm just factoring this quadratic. Again, you might have learned a different method for this, but it's all the same. So factor this however you like. I'm going to say this is probably negative 6 and positive 1, because yes, that is correct. That adds up into negative 5. So maybe a box method is what you would do here. Again, world's your oyster on how you want to solve this. There's so many ways to solve quadratics. I'm going to split negative 5x into minus 6x and positive 1x. And then minus 3 is equal to 0. Now I'm going to group. So I'm going to factor each group. The factorization of 2x squared minus 6x is 2x times the quantity of x minus 3. And then the factorization of x minus 3, there's no GCF there. We just are factoring a 1. And you're leaving the x minus 3 on the inside. So from this mess, I can see that the x minus 3's are common factors. I can pluck that out. The other factor is going to be that 2x plus 1. Here are my factors. I can set these both to 0. And this will get me my 2x values where I have a solution. So it looks like I'm getting a positive 3 and a negative half. So if I want to satisfy this greater than 0 condition, I'm going to stick with the positive 3, because 3 is greater than 0, negative 1 is not. So what do I actually have to do? I have to come up with x plus y. So if I know x, all I got to do is plug it back in to solve for y. I know, so I'm moments away from finishing the problem. I know that y is equal to x squared. All I have to do is plug in this 3 for x squared. 3 squared is 9. My ordered pair solution here is going to be 3, 9. When it's asking for x plus y, it's simply just, so 3 plus 9, x plus y, you're going to get 12. And that was a bit of work. If this was a calculator problem, oh my gosh, this would be so much easier, right? I'm actually going to plot these on Desmos real fast right now just to show you what this looks like. Because I do think having like an algebraic intuition of things, or a graphical intuition of things is important. So this will be negative 5x plus 2y. And then that's equal to 3. So you'll see here, kind of similar to what I plotted, we see the 3, 9 here. This was the negative x solution that didn't work. So adding up these two values, you get 12. Perhaps that should have been the hard example. I don't know. Maybe the other one would be easier for you. This one I couldn't figure out which one I wanted to make the hard one or not. But a little bit of work involved. You had to know a thing or two about quadratics, which was a bit of a bummer. So maybe this should have been in the quadratics. I don't know. Whatever. Still good practice. All right. So for what values of k, so I'm looking at the next one, non-calc, multiple choice. For what values of k would make the given systems of equation have no solution? All right. We know that, and we should know. I'll do this in red. A system has one solution when they intersect. A system has no solutions when they're parallel. And then a system has infinitely many solutions when they're on top of each other. So this is me trying to draw two lines on top of each other. And I guess I can draw arrowheads too. So what's the deal here? I want to figure out when there's no solutions, right? So we're looking at this case right here. I want to create parallel lines. So coming up with the slope of the first one, so long as I get that slope, it's going to be the same slope as the second. And then I'm done with the problem. So yeah, maybe I actually should have flip-flopped these two, but whatever, I'm going to stick to this. So I'm going to solve for my slope here. So I'm going to get this first equation in mx plus b form because I want this k down below to have the same exact slope. K is in the slope location. If you look at the second equation, right? Y is equal to kx plus 12. I need to decide what the slope should be, which is k in this case. So I'm going to hunt down the slope on the first one. Not too bad of a process in terms of the algebra right now. I'm going to be moving the 2x over. So I get negative 4y is equal to negative 2x plus 12. And I'm going to be dividing everything by negative 4. Divide by negative 4, divide by negative 4, divide by negative 4. And I'm going to get y is equal to 1/2 x minus 3. Here's my slope. Wait, highlighter, please. Okay, well, okay, that's highlighter. I have a slope here of 1/2. That's what my slope is going to be in the other one. Should be also 1/2. If both slopes are a half, tragic love story of two lines that have everything in common but never meet. We end up getting D here. And okay, I'm still in markup mode. I don't use this software too often for writing on things. I usually use Word. So it looks to me like I'm going to get a slope of 1/2. So long as both of them are the same, they'll never intersect. So long as and they also have different y-intercepts, which they do. Here's a negative 3. Here's a positive 12. Okay, same slopes at negative or positive 1/2. So that's heart of algebra. Now, is that 100% of heart of algebra? No. There's some other things, like maybe basic stuff like writing super general expressions. There are other things, but in terms of like the equations you need to know and stuff like that, that's it. So we're kind of done with that category. That is a good, hefty, actually kind of majority in some ways of the SAT, because problem solving and data analysis, only 29%. Passport to advanced math, only 28%. And then your geometry topics are only 10%. So that's going to be majority of your test is going to look like that in terms of the topics, not overall. All right, so the next one here, kind of like statistics topics where they're not exactly statistics because you haven't taken a stat course yet. But there are some stat topics that kind of thrown into middle school and early high school that, like reading histograms, bar charts, or bar graphs, line charts, scatter plots. And you should know words like mean, median, mode. You should understand the general premise of probability. So long as you have general foundation of all of these things, you should be good, truly. Because the way that I wrote this last one, going to spoil some of the fun here. It's very clever because there's a lot of deeper statistics to it, but you don't necessarily need to know it. The SAT does this pretty often, actually. All right, so easy problem 1. Sure, we can use a calculator. That might be a trap. It is, and it's multiple choice. So the following scatter plot represents scores on a 15-question exam from individuals that studied for X hours. So X-axis represents hours, Y-axis represents the score. Which equation best models the data? Okay, so I have some sort of scatter plot, and I have 4 equations that may represent the scatter plot, or like kind of line of best fit might be the best fit to represent this data. I'm going to do my best right now to draw a line through this data just to get an idea of like, and follow your heart. Now, there's actually a very real process called like regression that's really truly behind this notion of coming up with a equation of a line that represents your data points. We don't need to know that for this. If you sat there, oh geez, please don't do this. If you know the actual process for line of best fit and you sat there and you found the exact ordered pairs, oh man, do not do this on the SAT. I just thought of that right now. That'd be a real shame if somebody actually does that. You're going to be wasting an enormous amount of time because look how many data points there are here. There's like 10 or so. Just entering that amount in your calculator and then going through the process of line of best fit, that actually should work, by the way. That actually should legitimately work, but please do not do that because typically when you do see a problem like this on the SAT, these equations are written so that you can like easily remove certain options. So here I'm going to easily remove two of them. Hello, is this line positive or negative? It's positive. I can remove my negative slope lines. Negative slope, negative slope. It's already a 50-50. Where is my line crossing through as an x-intercept down below? We see that my two options here are 10 and 3. And just the way I drew my line, you can see that I drew it such that it crosses at like 3.8. Well, okay, my line's not perfect. I eyeballed this. So which of the two options makes most sense? Crossing through 10 or crossing through 3? Well, it should be a little obvious that 3, without a doubt. I'm not crossing through 10 all the way up here. That's way too high. So I'm already done with the problem. Y-intercept was a little off in B. Done, moving on to the next one. Okay, so you could be given like a frequency table. I think this is called a two-way frequency table when you're given like columns adding up to a particular number. So adding down here, cable TV, 2 plus 16 is 18, 10 plus 6 is 16, 8 plus 8 is 16. And going to the right, I'm just making sure that these numbers are right. I don't think I did this when I made it. 2 plus 10 is 12, 12 plus 8 is 20. Okay, so it looks like I'm good here. This is 24. Oh, am I? This is 22. 22 plus 8 is 30. Okay, I made the table right. So the following table shows the results to a poll on how a group of adults watched an episode of a new series. What is the probability a randomly chosen person who watched on their phone is a young adult? Okay. Notice how I read that. And I know that I had the foresight of knowing what this problem was, but the linguistics in this section in particular, the whole problem solving and data analysis is actually critical. So I'm going to read that part one more time. Probability, a random chosen person who watched on their phone is a young adult. So of those, this is a conditional probability, of those that watched on their phone, what is the probability that they're a young adult? So what I'm going to do here is maybe in this teal color. So a randomly chosen person who watched on their phone. Here are people that watched on their phone. There are 16 people that watched on their phone. What is the probability that if they're randomly chosen that they're a young adult? The young adults of this column is 10. So 10 out of the 16. What is the fraction I can extract here? It's exactly that. Oh no, I don't see 10 over 16 as a choice. It's called reducing a fraction. We can divide both top and bottom by 2, and we get 5 over 8, bringing us to solution C. So a lot of these other, feel free to play around with this, a lot of these other choices are like very deliberate distractors, where like maybe you thought it was 10 over the total number. So 10 over 50 is a fifth. So you see that that's choice A. So oftentimes these multiple choice questions, not even oftentimes, I want to say like 100% of the time, the other choices are intentionally misleading, intentional distractors. They write problems in these ways for a reason. To trick you, really. I mean, really, actually, because they want to see who's not going to get tricked and who's going to get tricked. All right, so speaking of tricks, here's honestly the trickiest one on this entire packet. And maybe I shouldn't start things with that premise. Whoops. All right, so hard example here. You can use a calculator, sure. I hardly see any numbers, so you're not going to touch it. Multiple choice. Company is trying to gather information on their service and surveyed 100 customers from the same town on their services. 83% of the customers said they were satisfied. Which of the following statements must be true? So we see here, like, before I even read the problem, you should have saw the solutions where, okay, it's like one of these things with like the Roman numerals, like, okay, it could be 2 and 3, could be 1 and 3, could be none, could be one of them. So if we look at the first one, let's go through each one and see if they're true or false. So I'll do green for good and maybe red for bad. So for the first point, if 100 adults from a different town were surveyed, 83% of the customers will say they're satisfied. So I see different town here. So maybe this is like a cable company, and maybe in one town, excellent service, in another town, terrible service, because just not a lot of, like, I don't know, like Wi-Fi, land, I don't know stuff about like cable and internet. We know that it varies per location, for sure. So if you just simply go to a different town, like a rural city or a rural area, they might not have that same exact customer satisfaction level. So as a result here, so I don't like that I used green. This is not what we want. So different town, that's suspicious. I'm going to go with no on that one. So we can actually already eliminate choice C. All right, so the second choice, or the second kind of scenario, out of 100 randomly selected customers, 83% are satisfied. This one's really tempting. Like, super tempting. Like, why not? Like, here in this town, 83% were satisfied, so if you just select another 100, sure, wouldn't it also be 83%? Not quite. These 100 people in this town do not represent everyone. In fact, these customers need to be independent. They need to, like, not have the same like anything in common in some ways. Like if you are going to fill out like a random customer service thing, it needs to be sent out to absolutely random people. It can't be sent to people in the same town if you're doing like a whole like nationwide service or something like that. So not necessarily. No, of 100 randomly selected people, there, like, sure, it might be 83%. There's this is where you would create like confidence intervals, and you would maybe do like you would map like a t-distribution, and there is some real statistics to this, but really what this problem is challenging us on is like the strict and rigorous linguistic nature of it. So of 100 randomly selected customers, no, it doesn't necessarily have to be 83% satisfied. So I'm going to cross that one out again. So actually, I do already have my answer off of that, because if 2 can't be right, you're going to see here that this is actually none. If we look at the last option, 83% of their customers are satisfied. Not quite. This is just from one particular town. You can create some sort of confidence interval, like we're 95% confident that 83% of our customers are satisfied, but we cannot say definitively that these are the same cases. So this was very tricky because they were playing with your expectations of like, come on, at least one of these has to be right. But that was clearly not at all the case. Okay, so for our next topic, or subtopic, we have proportions, percents, and ratios. It's still a part of the problem solving and data analysis piece. Algebraically, I can't come up with any sort of equation to give you because there aren't any. You just have to understand the connection between proportions, percents, and ratios. So if you're given like some sort of like 1 mile is approximately 1.6 kilometers, the ability to convert units is a skill here. It's usually something boring like a table about trees, and usually has a massive amount of reading, and it's never fun to do. Setting up proportions is pretty common, usually wordy. These are my least favorite. These are without a doubt my least favorite. Okay, so let's look at the first one. On the alien planet Fluxion, the Great Tower of Bicepton is exactly 120 maskeles tall. What? So this is not uncommon on the SAT to just be thrown into this ludicrous scenario where it almost doesn't even read as English, and in here it certainly does not. These are all made up words by me. Flexion, biceps, let's go. So 120 maskeles tall. I have this tower that's 100, okay, whatever a maskele is, sure. The length of a maskele, okay, this is important to know, can be converted to 3 pumplins. Let's set up like a conversion. 1 maskele is equal to 3 pumplins. Okay. It's already tempting to like want to throw this into a hard category, but it's actually not, so long as you can kind of like throw yourself into this situation rapidly. And you can kind of withstand that whiplash. So how tall is the Great Tower of Biceptines in pumplins? If we know that it is 120 mesquiles tall, we can set up a proportion. So how many pumplins? So it's 1 mesquile for every 3 pumplins. So for 120 mesquiles, it's x pumplins. We can do cross multiplication here. 1 times x, 3 times 120. X is going to equal to 360. And you can see I miswrote this, but I'll fix it when I upload the document. Looks like my choice here is C. So what were the other distractors? Kind of if you set up that ratio wrong, if you did like 120 divided by 3, you would have got 40, stuff like that. Okay, this one is a fun one. So we have a calculator active and it's multiple choice. Rectangle has an area of 36 inches squared. It needs to keep the same area, but decrease the length by 25%. What must the width increase by? Oh man, this feels like a headache of a problem. Especially, imagine, you're on the 5th hour of the exam and it's on the calculator portion, so that actually comes last. And you're just like, man, this seems like a simple problem, but maybe there's some sort of aspect to it, because it's really tempting to just say, well, the width must increase by 25%. And I see a 25% as my literal first choice. It's 25%, right? No. All right, so we know that the length times width represents an area of a rectangle. In this case, it's equal to 36. So if we decrease the length by 25%, that's 75% of what it used to be, right? 100% minus 25%. Okay, my length is going to go down to 75% of what it used to be. So I'm going to replace, I'm going to switch to maybe blue here. I'm going to replace my length with 0.75 L. And then I need to change W to some capacity, right? Something's going to happen to W. So maybe in W, I'm going to kind of put like a question mark W. Like what percentage increase do I need for W in order to get this 75%? Or in order to keep 36 as my my overall area. So what I can do here is I can, well, all right. In the equation above, I know that my width is equal to 36 over L. So my kind of like new width, like what I'm scaling my width with, is going to be equal to 36 over 0.75 L. One way we can think about this, 36 divided by 0.75, we can just type into our calculator. Another way is you can multiply by the reciprocal if you'd like. 36 times the reciprocal of, well, I know that 75% is 3/4, so I can do times 4/3. So that would be 48. So my new width is going to be 48 over L. This is there's another way of doing this that I'll also show. So if I know that my width is equal to 36 over L, I can just plug this on in. This is kind of a processed way in hindsight. 36 over L is plugged in for W. And this is going to be equal to 48 over L. I can divide both sides by 36 over L. So that new kind of fraction that's going to be sitting in front of W, or a percent, is going to be 48 over L and then 36 over L. The L's will definitely cancel, and I'm going to get 48 over 36. 48 over 36 can be reduced to 4/3. So if we want to figure out how much it's going to increase by, this would be 1 1/3. It's increasing by 1/3, which is 33%, 33.3%. This is technically the way they want you to go. And just like a problem we did earlier, and I wanted to show like the abstract way because I do think the math is kind of cool here, but don't worry, I'm going to show you a shortcut to this. In these situations, I do truly think it is best to do what we did above and to just kind of plug in numbers, play around with numbers and see what happens. If we would have done that, it would have been a lot more straightforward. You're probably sitting there right now, or a lot of you maybe, like thinking, oh man, that is not something I want to reproduce. I don't blame you. How about we just consider scenarios, okay? So we know, so this way is kind of the, I'll say official way, but here's the thing. You're working with Math Man McGreal. How about I show you just a better shortcutted approach? Shortcut. We know that length times width is 36. What are some numbers that can multiply into 36? 4 and 12. Not 4 and 12, 4 and 9. 3 and 12 would have worked. Actually, and you could play around with this with 3 and 12 if you want to as well. I'm going to say 4 times 9 is equal to 36 here. So if I decrease, say, the length of 4 by 25%, what is 75% of 4? 3. So this would go down to 3. So what must this 9 change into? This 9 must change to, well, I can divide both sides by 3, 12. How do I get from 9 to 12? The ratio 12 over 9 is 4/3. That is your 133.3%. There's your 33%. It's still not an easy problem, don't get me wrong, but it's a little bit easier when you play around with actual tangible numbers, because when you play around with abstraction, it feels a lot heavier than it actually is. It's still not an easy problem. Hence why they're my least favorite. All right, so the next one, it is the hard example, and it's labeled as hard because you got to read, lots of reading. So a survey was conducted at Eastwood Elementary School, and it's to decide which hot lunch option was most favored by the students. The elementary school is home to 496 students from grades 1 to 5, and 1/8. Okay, so there's going to be a lot of scenarios here, and we got to slow down. It looks like I'm going to get a numeric answer. Okay. 1/8 of those surveyed were first graders. So there were twice as many second graders as first graders. I see where this problem's going. I'm going to need to add up to 496 in some way by adding up all my first graders plus all my second graders plus all my third graders, all my fourth graders, all my fifth graders. First, second, third, fourth, fifth. All right, so I'm going to go back to the moment it said 1/8 of those surveyed were first graders. So I would need to find 1/8 of 496. And I'm going to use a calculator for that. So you're not going to see me type it in, but I'm just doing 496 divided by 8, which is 62. There were twice as many second graders than first graders. So that would be 124. Okay, that wasn't too bad. There were, okay, so 1/4 of those surveyed were in third grade. So I got to find 1/4 of 496 now. So divide that by 4 instead of an 8, and you get that 124 again. So looks like the same number of third graders and second graders. There are the same number of fourth graders as fifth graders. Okay, so I'm just going to put X for these, and that's maybe what I have to solve for. If every student was surveyed, yeah, how many fifth graders are there? We're just solving for X. So what made this problem hard? And again, maybe this would be a perfect scenario where these could have been flip-flopped depending on who you are. If you're someone who doesn't mind reading, see, I mind reading. Reading is, that's usually what gets me on the SAT. Problems like this, you know, number sense is kind of natural to me. So I did like this medium one. But maybe you're someone who likes reading and these two in difficulty would be flip-flopped. Because at this point, this is just a linear equation. I can add up 62 plus 124 plus 124. Don't know what that is, but I'm going to do that right now. It's 310. Oh, you can see that. You can see some part of my screen there. So it'll be 310 plus 2x, because there's two x's there. Subtract the 310 from both sides. You're going to get 2x is equal to, you can hopefully do this mentally, 186. So there's a 186 right there they're trying to bait you with, but divide both sides by 2, you get x is equal to 93. So solution here is B. Lots of reading on these portions, where's my cursor? Hello? Yeah, these problem solving and data analysis problems. Usually they throw you into like some ludicrous scenario and you just got to figure it out. But sometimes it's just general. I like, this is actually secretly my favorite problem on here, but I think probably for a lot of us, maybe it's your least favorite problem so far. Some of these problems here I designed to be a little bit harder than what you might see. Some of them may be a little bit easier, but the general overall difficulty I'm going to say is spot on, plus or minus. Okay, so we're now moving on to the passport to advanced math topics. And these are a little bit more involved in terms of the algebra, but in terms of the reading, oh man, thank God, there's a lot less reading here. So that's going to help us out, help me out maybe. All right, so vertex, intercept, standard form, know these three. H and K is your vertex and vertex form. P and Q are x-intercepts in intercept form. And standard form, I didn't write it here, but maybe I should have. You should know that x is equal to negative b over 2a for standard form. This is your vertex. You can even see it if I highlight it here. Negative b over 2a in the quadratic form setup. All right, so it's a parabola visually. And some words you should know: quadratic, parabola, vertex. Axis of symmetry, so that's just when you're symmetric. So here the axis of symmetry would be 0. And be able to identify quadratic units. So sometimes you'll see like a projectile motion problem, and you might see like a meters per second square or something like that. Okay, so what are the solutions to the following quadratic? So this is an easy example because it's straightforward. Is quadratic formula, which is what we're about to do, necessarily easy? You know, your miles may vary. So non-calculator, unfortunately, we can't just throw it into a program that does it for us, because I know a lot of you guys have that, and it's multiple choice, so at least we can kind of work off the answers. I can see here that this quadratic is not going to work out nicely. I'm going to say A is 3, B is negative 2, and C is negative 4. So I want to use my quadratic formula by plugging in these values. You are not provided the quadratic formula, so you should probably memorize it. There's maybe like a 50% chance you'll need it. I'd say like maybe half the SATs I've seen have like some moment where it would have been useful, and then maybe the other half literally just didn't have any moment. So feel free to gamble if you'd like, but I don't think it's too crazy of a formula to memorize. So I'm plugging in a negative 2 for this negative b right here. So this is going to be a positive 2. Plus or minus b squared, so negative 2 squared is 4, minus 4ac, so 4 times 3 times negative 4. And this is going to be all over 2a. If my a value is 3, then 2a is going to be 6. All right, 2 plus or minus, let's see, what is 4? Minus 4 times 3 times negative 4. 4 times 4 is 16, so 16 times 3 is 48. And it's going to be positive. So 4 plus 48 is a number, 52. So I'm going to get 2 plus or minus root 52 over 6. We can see here that we have some options with those 52s in the radical. And then we have some options with 13s, which may suggest I have to simplify this radical. Can I break down? So I'm going to just kind of pluck this root 52. Is it possible for me to break down the square root of 52? It sure is. I would divide out your perfect square factors. So the first number always worth testing is the number 4. Because in a lot of cases, it's the easiest to create that. If I try dividing this by 4, I'd have to do it mentally because it's non-calculator. 52 divided by 4. And that's not a square root. That's division bar. Okay, it goes in once. I get 12, goes in 3 times. It works out. It checks. It's 13. So I can break this into 4 and 13. Because, well, why would I do that? The square root of 4 is 2. This is the same thing as 2 root 13. So I'm going to plug this back on in. And I'm almost done. I'm like one step away. I'm going to get 2 plus or minus, and I'm going to go back to pink here, 2 root 13. So I just simply rewrote that root 52. And this is going to be all over 6. Can I do some simplification here? I sure can. 2 over 6 is a third. So just remember to divide this 6 by both your terms here. So this is going to be 1. 2 over 6 is 1 over 3. Plus or minus, the 2 over 6 here also reduces. There are 2 terms in this numerator. So it'll be plus or minus root 13. And this is going to be all over 3. So do I have a 1 plus or minus root 13 all over 3? I sure do, and it's C. So this was actually just straight up why was this easy? Why did I label this as easy? It may not actually be. There was a lot of algebra we did here. There's no tricks. The SAT didn't try to trick you in this one. It was just like, hey, okay, here's a little lob. Can you just do the quadratic formula? All right, next one, calculator active, multiple choice. On the xy plane, I have this parabola, negative 2x squared plus 8, and it intersects negative 2x plus 4 at 2 ordered pairs. Okay, we kind of saw this a little earlier. So what is the value of a plus b? If we notice here, a is the x value of the first solution, and b is the x value of the second. This is actually, it's actually pretty rare that you're going to access the graph portion of your graphing calculator. This would be an example of one I would absolutely do. So I would graph this in your y is equal to, plot both of these, and actually solve. You don't necessarily have to do it that way. You can set these equal to each other and factor, but we see that this is calculator active. So, sometimes the calculator is actually, it's not like every single, 100% of the calculator problems, it is inefficient to use the calculator. No, not necessarily, but in a lot of ways, they actually more often are than not. This is just a good, nice example where if you did type this into your TI, which I don't have that software on my personal PC, by the way, so you can graph this on your own if you'd like. But I'm just going to use Desmos because it is free and easy to use. I see they intersect at negative 1, comma 6, and at 2, comma 0. So the x components are negative 1 and 2. So here this would be, and maybe I'll just for the sake of having this key, or having this sort of keyed out. Here's my parabola. Here are my intersections. So the a value here was negative 1, and then my b value here, it's the other x component, is 2. Just take the x components. So if we plug these in, I'm getting the absolute value of, negative 1 plus 2. Oh, that was supposed to change colors. I'm just getting 1 from this, and that's my answer. So there are times where your graphing calculator can actually be used for graphing. It is once or twice. I know it seems backwards, but it's what it is. Okay, this one maybe we can use a graphing calculator on, maybe, but also can be done algebraically. This one's going to be a little involved. So the quadratic equation below is a parabola with vertex 1, comma k. Which of the following is equal to k plus p? So I have this, oh boy, all right, so some work's ahead of me. I have this in intercept form. Negative quantity of x minus p times x minus 2. I want to somehow extract the vertex. So if I think about all the forms I know and love, I could put this into vertex form if I'd like, or I can convert it to standard form and use the negative b over 2a expression. I can use either of the two. I'm going to do the second approach because it's easy to convert from intercept form to standard form. So that's what I'm going to do. I'm going to write this in standard form by distributing this out. So x times x, I'm going to keep the negative in front. X times x is x squared. X times negative 2 is negative 2x. This is where things are going to get weird. Negative p times x is negative px. And negative p times negative 2 is positive 2p. I can distribute the negative in. So I'll get negative x squared plus 2x plus px minus 2p. And what else can come from this? I can get this into this ax square plus bx plus c format, standard form, by kind of like factoring the 2 and the p here. Like factoring the x out. And I'll show what I mean by that. If I factor the x out here, I'll get x times the quantity of 2 plus p, and then minus 2p. This is it. These are already in the same form, but it's more conventional to put your number in front of x, right? Instead, like 3x, instead of writing it as x times 3. So I'm going to write this as negative x squared, and then plus quantity of 2 plus p times x minus 2p. All right, so why would I convert it into this form? I know that the vertex can be found. So this is the equation for axis of symmetry. I put vertex here, but it's axis of symmetry. This negative b over 2a is the x component of your vertex. So I'm going to do exactly that. I'm going to use this negative b over 2a expression to get the x component of my vertex, which I know to be 1. So I know that 1 is equal, and actually I'll do it this way. I know that my x component of my vertex is 1. So maybe the stars are kind of aligning here. I'm going to plug this in for this x. So I'm going to put a 1 here. I also know what my a and b value are. I know that a here is equal to negative 1, and that b here is equal to 2 plus p. So I'm going to plug these in for my values respectively as well. I'm going to get negative quantity of 2 plus p over 2 times negative a. And what do I get from this? The negatives cancel. So I get 1 is equal to 2 plus p over 2. P must be equal to 0 here, because I'll get 2 over 2, which is 1. But I can also solve it the long way. I can multiply both sides by 2. And I get p is equal to 0. Okay, so at least I have, so check, I have one of the pieces of my puzzle here. P is equal to 0, check, check. I gotta find k though, so I need to plug this 0 back in to get what my equation is actually equal to. And then I'll plug in my 1 to find my y component of my vertex. This one's probably a little bit harder than one you'll see on the SAT, but really try to appreciate what I'm doing here. I'm trying to get you like refreshed on not only all the aspects of every problem, but you know, a little bit of training in the process. So I know that p is equal to 0, so therefore y, and I'll kind of show my work on this one. I'm saying, well, I know that p is equal to 0, so I'm plugging in 0 for that. So y must be equal to negative x times x minus 2. Okay, so that's the same thing as negative x squared plus 2x. If I want to plug my 1 in to get my, so I'll write this as y still for now. If I want to plug my 1 in to hunt down my y, that's actually not that bad at all. I'm going to write f of 1, just because that's what I'm plugging in. Negative 1 squared plus 2 times 1. Actually, this is calculator active too. I could have graphed it at this point because I can just graph. Yeah, I mean, literally, I'll just do that right now. I know what the equation is. It's negative x squared plus 2x. So negative x squared plus 2x, done. It's 1 comma 1. But so my k value is 1 here. But you know, if I do it this way too, this is also fine. I would end up getting 1 plus, I was plugging in, the negative's on the outside. And that's like a cardinal sin of quadratics I just committed, but I caught it at least. This negative was on the outside. I shouldn't have put it on the inside. So negative 1 squared, or 1 squared is 1, and that's going to be negative 1. 2 minus 1 is 1. We end up seeing that these are the same numbers. So what is my k equal to? K is equal to 1. So 1 and 0. What is 1 plus 0? It's 1. Was there a faster way? No. The reason why is because the way that they kind of like encrypted their answer. They wanted you to find k plus p. If they wanted you to just find p, there could have been a faster way. You could have plugged and chugged and just tested all the values. But they intentionally had you find like two kind of different elements of it so that it was encrypted in a way that you couldn't just plug in numbers. So this was actually the fastest way of doing this one. Will say I wrote this one a little bit more challenging than what you might see, but it's good to kind of be able to handle this caliber, right? And certainly what is another moral of the story here? Knowing intercept form, knowing standard form, being able to convert between the forms, knowing negative b over 2a. These things actually do have some % chance of showing up on the SAT. So, if anything else, look at those kind of for like practical purposes for this. But I would say this one was a little okay. I had a lot of fun writing this one. I had a lot of fun writing this one, and I had a lot of fun writing this guy right here, the rectangle. So my students don't like it when I say I had fun writing this problem, because then they see what my version of fun is. Toning it back a bit. All right, so let's keep going with this. We're on to 7 out of 10 topics. We're definitely on like the 2-hour marker of this video. Exponential and radical. Okay, we are dealing with a times b to the power of x. This is your exponential curve function. And ideally, or practically, we might only see this like once, truly, maybe twice. The other end of it is like, okay, well, we can change our exponent by creating a rational exponent, like a fraction. And we see that in action for the second one here. So if you have like your index on the outside and your power on the inside, this can be written as a fraction p over q. And you might see this in radical form. You might see this in rational exponent form. So some words, exponential. So exponential functions are used to represent populations. So you might see some population over time t, growth decay, and you might see the word radical. So for this first one, it's straight up definition. So good, nice to have a little breather after that last one. If I'm using this definition right here, the qth root of x to the pth is x to the p over q. Same idea over here. If I have this exponent of 3 over 4, this will be the 4th root of x to the 3rd. So this is just by definition. Other way around. This is just this guy by definition. Very easy to flip-flop that. This is your root. This is your exponent. Choice B. Keeping you on your toes. All right, so for the next one, it's non-calc and it's free response. So we do have to just come up with a numeric answer. We have this like radical equation, and it's equal to 9. If x is equal to 4, what must the value of k be? I see these often, and I don't know why. It's like one added step. I think it honestly, like every time I say I don't know why, I think I kind of do. It's just to try to trip up like the 1% of people that might be tripped up here. I know that x is equal to 4. So just plug it in. So what do I have going on for me? I have the square root of k plus 6 times 4 minus 3. And this is equal to 9. 4 minus 3 is 1. So I have the square root of k plus 6 is equal to 9. Right? It's truly designed to trip you up, because at this point, I could have just given you this equation, right? But they just wanted that extra substitution step for, whatever reason. But at this point, the rest of the problem is kind of a normal situation. Square both sides. You get k plus 6 is equal to 81. And if you subtract 6 from both sides, you end up getting k is equal to 75. So that is that. You should check for extraneous solutions, but in this case, it's not extraneous. We have a positive number on the right here. So sometimes that would be very rare and unfortunate that happened. But if you have like a square root is equal to a negative number, I would be immediately cautious of that, because the square root cannot equal a negative number unless they say something about imaginary numbers there. But they typically won't do that in that context. Okay, so the next one, and you can see that these were a little bit faster. The next one here, population of bacteria is growing. It grows by 5.4% every minute. If at time t, or if at a time of 10 a.m., there exists exactly 5 million bacteria, which of the following functions represents our population of bacteria? B, in millions. In millions. This is super, super common, again, on the SAT, where they might have an equation that, or a table, could be a lot of things, or a graph, where maybe the y value is in thousands or in millions or something like that. So keep that in mind, what that would look like in real practice. So we're not going to have 5,000 in our equation, was what I'm trying to say. B is already in millions. So if you had 5 million in your equation, it would be 5 million million, which is a super ultra mega big number that I don't want to deal with. So right off the bat, I can actually, just looking off my answer choices, I can see that these guys are not going to be the way to go. So working off my answers here, clearly I have to write an exponential equation in this y is equal to a times b to the power of x setup, where a represents your starting amount, initial amount, and b is your growth or decay factor. So we have two choices now. We know that this is in millions. So I guess I can finish the rest of the problem. T is represented by minutes, and it's minutes since 10 a.m. All right. We have two choices. We can either take this 5 million and multiply by 5.4 every minute, or take this 5 million and multiply by 1.054 every minute. Let's think about how percents work. If we're multiplying by 5.4 every minute, that is massive. That means that you're going up by a factor of 5 times, a little over 5 times. That's 500% actually. If you're doubling, you're going up by 200%. If you're going up by if you're going up by 5, you're what's multiplying by 5? Quintupling? Quadruple, quintuple? Yeah, you're multiplying by 5. You're going up by 500% every time. Whoa, that is a bait option for sure. How do we convert like percent growth into a growth factor? What we do is we move the decimal place twice, and this would be percent growth, or this would be growth of 0.054 as a factor, but we're adding 1 to that because we are kind of like 100% of what we start at, and then whatever growth past that you're adding. So if you're going up by 10% every, we're going to the gym, first time you're going to the gym, and your lifts are going up by 10% every month. That might happen for like the first few months. Why not? You're increasing by, you're going up by 110% every month. You are 110% of what your previous strength was every month. So here, that's exactly what this idea is. We can think of it kind of as 1 plus 0.054 to get a growth factor of 1.054, or you can think of it as 100%, so you are 100% of what you are with no changes, plus 5.4% to get 105.4% growth. If you write this as a decimal, this would be 1.054, which is choice D. So either way of thinking about that is the way to go. I'm being a little extra explaining the concept. This is meant to be a refresher course, so I'm explaining some of the concepts, but at this point I would have stopped, right? I would have just saw the 5.4 and been like, oh, no way, that doesn't make any sense. Circle D, move on. Woo! All right. What am I at? Like almost 2 hours, like I said. Whatever. I'm going over like all the math you need for the SAT that you've learned in all of your years of education up to your junior year. So yeah, that's what it is. All right, so the 8th topic here, polynomial and rational functions. With the vertex, intercept, and standard form of quadratics comes the polynomial versions of them. So you can raise this to the 4th power, 3rd power, what have you. We can write polynomials in its factored form if it's factorable. And sure enough, polynomial standard form you might see. Rational functions are fractions of polynomials. So here are some example of polynomial graphs. You will pretty much not see a rational graph. And then here are some words you need to know. Most important ones are zeros, real zeros. I see that pretty often. Those are x-intercepts. Okay, so looking at the easy example, sure, we can use a calculator, not going to actually need it. Which of the following is true about the given polynomial f on the xy plane? So take a look at this function we're provided. And it looks like to me they're playing around with the number of real zeros we have and number of local extrema, being maximums and minimums in a local setting. So I see that this is how I actually want to handle this. In blue, I'm going to find my real zeros. Real zeros are x-intercepts. So I see there's 1, 2, 3. I can already cancel out these guys right here. In green, I'm going to do my extrema. Extrema are mins, or maxes and mins. So highest and lowest points. We can see that there's 2. So we can eliminate this guy right here. So 3 real zeros and 2 local extrema gives us choice B as an answer. So conceptual question on understanding these terms, really, from like an advanced algebra or algebra 2 course. Your junior year. Typically this is taught your junior year, maybe sophomore. Okay, next one. Given this polynomial equation, gotta maybe factor here. Oh, getting tired. What do I have left? Okay, I just have geometry after this. Okay, that's good. I got to solve this out, maybe factor. What is a possible solution? It's non-calc and it's free response. So yeah, certainly we'll have to factor here. All right, the way we should pretty much solve quadratics and above is get it to set equal to 0 and factor. So I'm going to move, I'm going to subtract the 12x cubed and subtract the 36x squared. I'm gonna just move them over to the left side here. So I'm going to get 3x to the 4th minus 12x to the 3rd minus 36x squared. All right, factor, factor, factor. What should we always look for first when we're factoring? You said it at home, you screamed it. Windows wide open. You said, look for the greatest common factor. Your neighbor looked at you thinking, what? Shut your window doors. Turn off your light. Run away. Left as a mystery. All right, let's find our GCF. If I look for greatest common factor, I notice all three of these terms have a 3 in common, and the way that we find a GCF of our x terms or our x components is we take the lowest power, right? You can't take x to the 4th here if this term has only 2 to spare. So I'm going to factor out my GCF of 3x squared. So what is this going to look like on the inside? X squared minus 4x minus 12. And that's equal to 0. Okay, so this 3x squared factor is going to produce a 0, actually with multiplicity 2, which I don't actually think you need to know for the SAT. Maybe. Just means that, okay, so if you have a factor that's squared, it means that it just bounces off, and I'll show you what I mean by that. It just means that it bounces off the graph. It doesn't pierce through the x-axis. So 3x squared, it's your basic parabola. It doesn't cut through the x-axis like a lot of normal zeros do. It just bounces right off of it. So we're going to graph this whole thing. I know it's just non-calculator, but again, I'm trying to refresh you on these things. How do I factor the we'll do it without it. We'll solve the problem without graphing it. What multiplies into 12 adds into -4, x minus 6, x plus 2. Usually you guys are pretty good at factoring those. So what are my zeros here? I get 2 zeros from this one. I get 6 from this one, and I get -2 from this one. So what is the answer to this? Well, if you have a positive number, your answer is 6, and you're done. But just for fun, I want to graph this and show you what it looks like. You'll find that this cuts through the axis at 6, and it'll cut through this other one, which was an intercept of 2, is going to cut through the axis at 2. Or -2, sorry. Here it is. There we go. So kind of bounces off the x-axis at that 0 moment because it has multiplicity 2. Any even multiplicity will do this. Again, I'm actually not sure if you need to know that for the SAT, but good to talk about right now. Pierces through at -6 or -2 and pierces through at +6. Okay. Next one looks like a rational expression. X squared plus 5x minus 7 is over x minus 2. It can be written in this form, I suppose, where you have some k's in there. For all x where x is not equal to 2, what is the value of k? To me, I see division of 2 polynomial expressions. And then here I no longer see that. I see like a little remainder right here. Sure enough, what we're going to need here is polynomial long division. So if I'm going to have this x minus 2 on the outside, I think synthetic would have worked too, but let's use polynomial long. And then on the inside, I'm going to have x squared plus 5x minus 7. Without a doubt, you learned this like junior year, maybe sophomore year if you're a little advanced. This is not something you learn early in your high school career. So what do you need to multiply x minus 2 so the way that polynomial long division works, what do you have to multiply x by to get to x squared? X. So you put it here. And then you subtract off the product of the two. X times x minus 2 is x squared minus 2x. And in a perfect world, if you do this correctly, these first terms will always 100% of the time cancel. So you're left with 5x minus a negative 2x, so that's 7x minus 7. Okay, I have a feeling I know the answer based on what I'm seeing here, but let's keep going. What do you have to multiply x by to get to 7x? We have to multiply by 7, so plus 7. And I'm going to subtract off that product. So 7 times x minus 2 is 7x minus 14. These should always cancel. And you're left with negative 7 plus 14, because it's double negative, so you get 7 as a remainder. So this is it. If you think what do you have to multiply x by to get to 7, you can't do that. This is your remainder. So therefore, we know that x squared plus 5x minus 7 over x minus 2 can be written as, so this is your remainder. This is just kind of what you bring back up top. It's still being divided by that x minus 2. This is equal to x plus 7 over x minus 2. So I'll go back to highlighter tool here, which I don't know why I'm so bad at. Whoa. This doesn't have an intuitive highlight tool. There we go. So here we see this k, here we see this k, here we see this 7 and this 7. K is equal to 7 here. Have to switch back to drawing tool. Okay. So polynomial long division, I don't know. I don't think you'll always see it, but there is some chance that you'll see it. Up to you whether or not you want to reteach yourself it if that was a little too much. Remember, this is like a boot camp course. I'm only doing this once. I'm not going to do this 20 times. But there is some chance that you might see this. I would say 50, just throwing a random number to it. All right, lastly, the geometry topics. And honestly, this is only 10% of the SAT. Geometry is such a small percentage. If you're taking the ACT, it's significantly larger. But SAT really, what does the SAT have more focus on when compared to the ACT? And I'm curious how much longer the ACT will be around. It's much more focused on this kind of stuff, languagey stuff, wordy stuff, words, and like general like reading a table and graphness. Like I give you a line graph, can you read it kind of thing. Some skills that you would actually kind of acquire in a science class sometimes, and less so in a math class. So those kind of skills a little bit more often on the SAT. Geometry, very rare. You'll see maybe a few. So don't break your back over geometry, truly. It's not actually worth it. But you might see like maybe 5 or 6 geometry problems, maybe a little bit more, but certainly less than 10. Okay, so what is the value of x here? Oh, okay, wait, let's actually look at so algebraically, you're actually given a reference sheet of all these geometry. Wow! So nice of you, SAT, to provide me with all these geometry formulas that are only useful for maybe 10% of the SAT, math portion of the SAT. How nice of you. All right, it's like, giving you like a bunch of tools for a job where, only 10% of the job requires those tools. And most of the other job, 90% of the job, you need your own tools for. All right. But I mean, I do agree with the philosophy of, do you have to memorize in real life all these geometry formulas? No, you can look them up. That's what I do. And then the other one that's not on this list is the equation of a circle. This one maybe shows up like, say, 2/3 of the time. I'll see like one problem of an equation of a circle. So be able to identify geometry visually, their shapes, and then, some very basic common geometry lingo like the angle A. Maybe you might see AB is equal to 12. That means side length is 12. Stuff like that. Okay, here I see a triangle, and hopefully your vision of 30, 60, 90 triangles is pretty good. They actually give you this formula too, right here, 30, 60, 90. So the way that it works, opposite to the 30 is a number. Opposite to the 60 is root 3 times that number. Opposite to the 90 is 2 times that number. So opposite to the 30 here is 12. So opposite to the 90 is 2 times 12, which is 24. 30, 60, 90 stuff. If just for fun, this would have been 12 root 3 here. Goes x root 3, 2x. Okay, next one. A circle on the xy plane can be represented by this equation. Which of the following represents the center? So I intentionally kind of wrote this to be a little tricky. We see the default form of a circle is x minus h all squared plus y minus k all squared is equal to r squared. You don't see any h. If there is a lack of presence of a number, what number numerically represents lack of presence? 0, right? It's not there. So you can write this as x minus 0 squared plus y minus 2 squared, and that's equal to, it might help you to rewrite your radius. In this problem, it does not, but it's a good skill to have. To rewrite your radius as 2 squared here. 2 squared is 4, because this is kind of telling me, I know now my radius is equal to this 2. It was not useful for this problem. So in this problem, what did we actually need to find? Center of a circle. Center is h comma k. So here is my h, here is my k. It is super tempting to give me 0 comma negative 2, but the default form of this equation is y minus k. So k is equal to 2 here, not negative 2, bringing us to an answer of 0 comma 2 for a. And for fun, because keep in mind, the point of this is not to just like do these as fast as possible, it's also to kind of learn. I will just graph this and show you what it looks like. X squared minus x minus 2 squared is equal to 4. Whoa, I put a minus, sorry, it was supposed to be a plus. Yeah, so that's what you get with conics. If you put minus instead of a plus in between the two, you get a hyperbola. Here you get a circle. And yeah, here's my center, 0 comma 2. Okay, last one here. So it's three-dimensional. A production company was ordered to mass produce cylinders with right cones, with the right cone with the same height and radius removed from the inside, subtracted. So if the diameter of a cylinder is and the cylinder of the cone is 6, so I'd make your radius 3. What is the volume of the shape? Okay, so I know that this is 3. We should come up with these formulas. So if you need to refer to the cheat sheet, you can, that they do give you. It's, so the cylinder is pi r squared h, and then the cone is 1/3 pi r squared h. So pi r squared h minus 1/3 pi r squared h is 2/3 pi r squared h. I simply need to just find the radius and height. So what made this problem hard? I don't know, it's kind of hard for me to come up with like a hard version of a geometry problem. They do exist, don't get me wrong, they do exist, but they usually exist as like composite 3D shapes like this. I will admit I wrote this one to be a little bit easier though, but you know, that was recompensated for in earlier problems. So you might see like a composition. I think one I saw like a silo. So it was like a cylinder, and then on top of the cylinder was a cone, and there was some other things that made the problem a little bit more challenging. So you know, your miles may vary here with what kind of geometry problems you get, certainly. So you get 2/3 pi r squared. I know that my r is equal to 3 here, so I'm going to just plug this on in for r. And then I know that my height is actually 12, so I'm going to plug this on in for h. And it is calculator active, so 2/3 times pi times, that'll be 9, right? Times 12, right? 3 squared is 9. I'm going to just slap this into a calculator because we can see all my answer choices are to the nearest hundredth. So if you don't mind, 2/3 times pi times 12 times 9, you get 226.19. That would be choice C. And you can at least see the result. You don't see what I type, but okay. Last one. Very, very long refresher, but it's everything, okay? I think this is worth the time. So for the angles and trigonometry aspect of things, you should know 360 degrees in a circle, 360 in a quadrilateral, and 180 in a triangle. SOHCAHTOA is your best friend. If you're going to see any trig, which you'll probably see like 2, is my guess. You'll see like 1 or 2. I very rarely see 0. I usually see 1 or 2 trig problems. SOHCAHTOA is the way to go. You don't need to know like double angle trig identity if you're that far in your math career. You don't need that. You need SOHCAHTOA at most. SOHCAHTOA, the way that works is that the sine of an angle is equal to the opposite over hypotenuse as a ratio, so on and so forth for cosine and tangent. You might see like a trig graph. You don't actually have to know how to graph trig functions, but you might see, like, you might have to interpret like a graph, and usually the answer is something along the lines of it goes up and down periodically. That's essentially what a sine wave is. A lot of words for angles, right? You might need to know acute, right, obtuse, equilateral, isosceles, and scalene, all for triangles. What else? Supplementary angles add up to 180, complementary 90. Vertical angles are congruent, same with like alternate interior and corresponding, if you remember those words from your geometry days. And then, of course, being able to understand, okay, sine, cosine, and tangent are different functions. Okay, if you can't tell, I'm getting a little tired, but these are the final 3. All right, calculator active multiple choice. Find the value of x. I notice I have parallel lines. When I have parallel lines, this is when alternate interior, corresponding, all those words come into play. It's been a minute since I've taught geometry. But what we should do here is we should identify that, all right, looking for x, find the value of x. Take a look at this little angle right here. So it's super tempting to just say, okay, 4x plus 10 is equal to 110. That's not quite true. But what we could see if we kind of tilt our heads here is that we have a straight angle. And we're going to create with this what's called the transversal, which you don't need to know, this line that cuts through 2 parallel lines. If this is 110, the other side must be equal to what? Should be thinking to yourself. 70. Right? How do I know that? Supplementary angles add up to 180. If I have a straight angle, right? And I can draw like a picture of this. This is 180 degrees, and this is 90 degrees. So if this is 110, this other side that doesn't look like a 7, but it is a 7 for 70 degrees. Now what I have, if you can kind of think about what I'm thinking, the angle that is 70 degrees actually looks very similar, right, to this angle that is 4x plus 10. That's because they are congruent. They are... Oh man, what are the words? Corresponding angles. They are corresponding angles. So corresponding angles are congruent. Remember that stuff from geometry? All those different angle, parallel lines stuff. They're the same. So we're going to have 4x plus 10 is equal to 70. And okay, everyone can solve. Well, you know, this isn't too bad to solve, right? Move the 10 on over. We get 4x is 60. Divide both sides by 4. X is 15. Done. All right, last 2. This one is trying to be harder than it actually is. Which of the following must be true? So I'm given this diagram, again, 2 parallel lines. And given some angles, x, y, and z. Actually, this is a lot of the same stuff from the last problem, just kind of embedded to look harder. If I know that this angle right here is equal to 180 minus z, well, I notice a straight angle again. This angle here must be z. This angle is also z. Reason being, z plus 180 minus z is equal to 180. So trying to be a little tricky there, but it wasn't too bad to catch. So I know that these are both z. And I know that I have this x and I have this z over here. So can I force a relationship between these lines? We kind of can, because we have this transversal that's cutting through in this direction. I don't really like how I drew that line. We have this transversal cutting through in this direction as well. We can actually force a relationship between z and y here. These are alternate interior angles. Z and y are the same. Likewise, we can create a relationship between z and x here. They are alternate interior angles. Z and x are the same. So if z is equal to y, and z is also equal to x, by transitive property, x is equal to y. They're the same. And this is just it. I always go to like this go-to example. Maybe z is Mike. If Mike is equal to Michael, like y is like a nickname for it, and z is equal to x, and Mike is equal to Mikey, then Michael is equal to Mikey. It's all the same person. It's transitive property, just with names. All right, so x and y are the same. Which of these equations would best represent x and y being the same? It looks like we have all these crazy relationships between them, but really one of them stands out as the most obvious. So try to think about this before I kind of just reveal the answer, because I don't really know a better way to navigate about it. If I know that x is equal to y, then the difference between them is 0. Actually, take a look at this equation right here. This is the answer. If I add y to both sides, hey, that is the same thing as x is equal to y. They were just trying to be tricky. But we can see through the weeds in the way, and we can see that this is just the same exact statement as that. So try to be a lot trickier. I mean, that's really what the SAT is in a lot of ways. Is like, hey, take the same stuff you learned throughout your high school and middle school career, and let's just add some spice to it. All right, so it is time for our very last problem. So sad, but also so tired. I've been doing this in like one go, and I've had like 3 cuts because I've made some small mistakes writing it, which will be fixed in the document below if you're still here. All right, triangles JKL and XYZ are shown below. It is known that JL is congruent to ZY. Let's mark these up. JL, ZY, and KL is congruent to XY. So KL, XY. Nothing too crazy so far. We can actually even say that these triangles are congruent. We can say that triangle JKL, you don't have to write this, you can just acknowledge it though, is congruent to XYZ by side angle side. Remember all those things, angle side, angle side, angle side. Sure, I mean, they pretty much look the same too, right? So what can we kind of deduce? That we have some angles that are congruent and some sides that are congruent. So like angle K here, which we may or may not need, is the same measure as angle X. All right, so which of the following ratios is equal to JL over JK? Let's break it down this way. This is not a bad way of breaking it down. JL is long leg, and on the other side, it's congruent to ZY, which is long leg on the other side. Short leg is KL, short leg, which on the other triangle is XY, short leg. And then lastly, you do have hypotenuse, so I will do that in blue. Hypotenuse and hypotenuse. Okay, because what am I kind of picking up here? Okay, I cannot spell anymore. Hard time doing that in the first place, but I'm a little tired now. We have hypotenuse on both ends. Okay. I'm just noticing that we're creating ratios of sides. And we have 2 congruent triangles, so we just have to come up with that same exact ratio. This is secretly trying to be a trig problem. So if I have this JL over JK, this would be in reference to, you can do it in reference to angle J or reference to angle K, but you can see I already kind of marked up K, although I do want to make that a little bit nicer of a angle looking thing. Here we go. So in reference to K, it's actually the opposite over the hypotenuse. SOHCAHTOA stuff maybe, right? So JL here, so I'm going to go back to pink, is long leg over hypotenuse for this angle K. So yes, SOHCAHTOA can actually be forgoed here in some ways, but I do want to use this as kind of a refresher to it. So let's just kind of solve it this way for that reason. I have this angle K here. I'm going to just say the sine of whatever this angle is, I'm going to call it angle, like A degrees, whatever, is equal to opposite over hypotenuse, long leg over hypotenuse. So that would be JL, which is what I had to begin with, right, in the problem, over JK, again, what I had in the problem. So what about on the other triangle? How can I come up with this same exact ratio on the other triangle? Well, I'm going to be looking at angle X instead because those are congruent. So same story. This is also equal to, since they're the same angles, well, opposite over hypotenuse. Opposite is zy. So I'm going to do this in pink here, zy. So here's the opposite in pink over hypotenuse. Opposite over hypotenuse. It's going to be xz. So you can see I kind of made a mistake, but I will fix it for the document. Which of these is zy over xz? We have ourselves a winner at choice A. Thusly ending our SAT review. All right, so was this 100% of the problems you'll see on the SAT? No. Honestly, it was probably a good like 70 to 80% though. What is the other percentage of problems made up of? Honestly, mostly like heart of algebra stuff. So scrolling all the way up. There are other examples I can that I could have shown you, but I wanted to make it a perfect 10 for like heart of example-esque problems. But they're pretty quick. They're just like setting up. Maybe you're given like a context and you're just expected to write an expression that represents that context or something like that. And maybe there are some more like general problem-solving problems I give you, but I can't really like package them up in like a nice niche, nicely knit package like quadratic functions or exponential and radical functions. So, but this is a lot. This is truly a lot. So I hope you benefited off this. Good luck on your SAT. And please continue to math on. I will do the same. I'll see you in the next video.